EDA's top executive map out an AI-driven future. AI is accelerating the need for 3D ICs and digital twins and causing lots of disruption along the way. Artificial intelligence is permeating the entire semiconductor ecosystem, forcing fundamental changes in AI chips, the design tools used to create them, and the methodologies used to ensure they work reliably. This is a global race that will define nearly every domain over global race that will define nearly every domain over the next decade. In presentation interviews over the past several months, top EDA executives converged on the three major trends that will become a focal point for the foreseeable future. AI itself is expanding from tightly controlled machine learning to assign AI assistants and generative AI and agentic AI. The shift requires processing of massive amounts of data in order to create the large language models and algorithms. And because of the limitation of scaling, it's driving a shift to multi-die assemblies. The best option is 3D ICs. Chips and systems need to be monitored throughout their lifetimes to ensure the reliability. AI is prone to hallucinations, and a complex system filled with chiplets can degrade over time in unexpected ways, resulting in silent data corruption, incompatibilities from the software updates, and accelerated aging based on changes in workloads. Artificial intelligence, the use cases for AI and EDA have evolved significantly from simple pattern recognition to assisted design and broad knowledge sharing, enabling engineers to get up to speed more quickly and veteran engineers to expand into new areas and be more productive. The way that we were describing it, you've a copilot and you've assisted and you've creative, said Assassin Gazi, President and CEO of Synopsys. Assistive is where you have a workflow assistant, a knowledge assistant, a debug assistant, so that you can ramp up a junior engineer in a much faster way, as well as an expert engineer. They can interface with our product in a more modernized, efficient way. Then you have the creative element. We have a number of examples where we have early customers engaged from the RTL generation, test generation, and test assertions, where you can have a copilot that helps you create a part of your RTL. Test bench documentation and test assertion. Yaji said that with creative tools, various tasks could shrink from days to minutes, but all of that needs to be tightly controlled. We cannot have bottles that hallucinate, he said. We are very deliberate about when and how we engage with our customers to make sure that the maturity of what we are offering is acceptable, without putting any part of their workflow at risk. As the AI continues to evolve, so will the workflow. I often get asked, the question from our investor stakeholders on when do we see a change in EDA as a market by leveraging AI? I don't believe that we will be the case unless their workflow changes, meaning you can do certain things very differently in order to a product roadmap in a faster, more effective, more efficient way. Now with the agentic AI era, agent engineers will collaborate with human engineers in order to take that complexity and change the workflow. Providing AI lives up to its promise. The magnitude of this change cannot be overstated, but all of this is evolving so quickly that it's creating a lot of questions for which there are no clear answers today. Time will tell what AI can do well, what needs to be closely monitored, and where the risks are. Prediction of AI the transformative capabilities have proved over optimistic since the late 1950s. But over the last couple years, starting with the rollout of ChatGPT, it finally seems to be living up to its promise. Agentic AI is the next big target. Agentic AI is an interesting concept. We are confident enough to trust the level of autonomy for the AI to open make active decisions on its own, said Michael, CEO of Siemens Digital Industry Software. In the design space, as we start talking about agent AI versus agentic AI, it depends on who you are talking to and how they want to slide the different term. With agent AI, from our perspective, we define a task with a set of the boundary conditions and the data AI operates with that box in order to drive to a solution. When you go to agentic AI, basically you are saying, here are the problems. You think about what is the best way to execute it. You come up with that solution and you go drive toward the desired outcome from an EDA perspective. This is how we look at the evolution of AI into our tools. The rate of the adoption is unprecedented. It's hard to find an error in chip design where AI does play at least some role, whether directly or indirectly. It's a profound change for our industry, said Niels Fischer, Vice President and General Manager of Keysight EDA Software. As we move through the simulation domain and physical domain, in all of these steps there is a data generated and there is a insight to be gathered. This is where artificial intelligence can be of great help. When we think about it from a simulation perspective, it can help us with the modeling. It can help us speed up the simulations. It can help us add more expertise to the product to help design systems. It can help designers to generate designs. It's very powerful and transformative. So years ago, a customer was telling me, I have a design team that they have spent a lot of time dealing with your product to simulate. I really want them to be designers, not simulators. The product design teams don't want to learn how simulators work, so they don't want to spend a lot of time setting up a simulation. They want to think about the requirements and how they can create a design from those requirements. That is the power of AI. It can really shift customers from how things are done to what they really want to do. AI can help you with routing on printed circuit board or to come up with the new topologies. Anirudh Devgan, President and CEO of Cadence Design Systems, compares AI to one layer and a three layers layer cake in EDA. For applications to be successful, they need to have all three parts, he said. There are AI agents and an orchestration. There is a principal simulation, and sometimes people forget how important that is. Each layer changes the behavior, molecular behavior, the fluid dynamics, the summer. There is no substitute for that. Then you have to compute to run it on. Looked at from a computational standpoint, AI seemed more evolutionary than revolutionary. When it first started, AI was dense computation, said Devgan. But the physical world is not dense, and the AI is not dense either. All the neural networks are not dense. So, what happens is that because of the complexity of the designs and the requirements, we innovate in all these algorithms. Then you have latency and partitioning and your hierarchy. You can see how some of that is in the top of in moving layers of abstraction and some in the bottom in the pure algorithms. Half of these algorithms are Boolean, 0 or 1, like a logic simulation or formal verification, and a lot of them are the numerical, like search simulation, characterization, and thermal. You need acceleration of both Boolean and numerical computation, and now with AI, we can do the next level of innovation in software. Both from a natural language standpoint and from optimization standpoint, AI is very good at optimization, and we have worked on it for several years. We have 5 major AI platforms: digital, verification, custom, packaging, and system analysis. And the results are actually quite phenomenal. AI can completely transform chip design, and that's why we are investing heavily in these 5 platforms. How EDA vendors utilizes AI varies somewhat, depending on the starting point. But one of the advantages of LLMs is their ability to span different data types, basically raising the level of the abstraction across the entire flow. So the starting point is less important than it might seem at first glance. The key is how they obtain and utilize the data and how far they can extend beyond just the design phase, something that will depend heavily on how data is shared and protected in the future and where companies see opportunities. As Siemens Elo explained, starting out in the generative AI space as the foundation because that's the first level where you've got a bunch of verified data sources from us and their custom data that goes into a data lake where you train an LLM. We have the ability to use various LLMs or customers can use their own. Then you can snap it into the infrastructure and use all of our tools on top of it. Given the breadth of the greenfield opportunities, picking the right opportunities is daunting. This is why the initial starting point needs to be relevant. How long does it take for someone to become the RF engineers? It's an art. It's an art. That excited fashion. It's not something you pick up in 6 months. It often takes years. But with AI, we can make information more readily available and accessible for designers. How can really close the gap between the productivity of a very experienced RF design and a novice engineer. Chatbots are an example of a way to provide information and right time in a better form to customers. The ID, 3D ICs. AI requires a lot of data, particularly for training models. The problem is that the planner's chips are unable to process all that data quickly and efficiently due to practical limitations, which is why many data centers utilize some sort of multi-die assembly, fan-outs, or 2.5D to boost the performance and reduce power as compared to a planar SoC. Figure 1. 3D IC conceptual model through interfoundry semiconductor engineering. But those are large incremental gains. Achieving orders of magnitude improvement in performance and power requires real 3D ICs, hybrid bonding, and arrays of chiplets. With 2.5D, you've got more flexibility as to how you structure the silicon such that it's more pliable for the software that it's running, said Hello. When you get to full 3D IC, your ability to partition more discretely across different die and to take advantage of different processes for optimization in that process for different functionality offers more interesting possibility for how the better its software workloads. It's intended to optimize, but it's still a little bit aspirational. Two key challenges are how to manage thermal dissipation and how to ensure the different layers can be bonded together properly so that densely packed interconnects line up perfectly. This is compounded by the fact that some chiplet in a 3D IC will be developed using the most advanced processes, while others may be developed at mature processes. Customers are already talking about the trillions of transistors, bringing them together in one package, while their schedule is a race to go from 18 months to tape out down to 16 months, 12 months, or below to deliver customized silicon for these intelligent systems, said Gazi. How do you deal with that? The complexity from the technology on a single die. We're talking about the GAA, angstroms in order to design that silicon, and then you bring it together in an advanced package. This is the only way to scale to hundreds of billions or trillions of transistors. But putting it together will be an engineering feat. The moment you start scaling to that level of complexity, you can only achieve the performance or power by being efficient at the interconnect level, Gage said. And dies may be coming from different process technology and different foundries. How do you verify and validate an architecture in order to deliver this advanced package? That also opens the door for both software IP, soft IP, and hard IP in the form of a chiplet. There are new opportunities, especially with 3D IC and I builder. So we are doubling down on our IP investment, said Devgan. The number of IPs we are offering and the number of process nodes we are offering has increased significantly. IP now is one of the biggest R&D teams in Cadence, and we will continue to invest in not just physical IP and interface IP, but also in Tensilica, which is widely used as an embedded processor. Digital twins. EDA vendors are acutely aware of the risk of AI systems and the unknowns in the 3D IC architecture. There is a need to connect, design and test and have a digital thread and verification from design to test, said Fashe. There are tools to manage quality reliability. And then, of course, there is a growing need for data management and analytics. All these tools need to be present, and customers need to move from homegrown tools to commercial tools. But these tools are also interdependent, so there is a need for a hub and a spoke models. Where the different tools can act on the data will evolve over time. They may consume data. They may generate data. IP is developed during the product life cycle. And so we need a backbone infrastructure for customers to be able to do that if we want to have a true digital transformation. The process of data management is crucial. This concept is still evolving, and so is the terminology. Some vendors call it a digital twin, while others call it a virtual twin. But the basic concept is real-time monitoring of a system to ensure it's behaving as expected, optimizing it whenever possible based on the workload, and taking action if something needs to be fixed before it becomes a problem. There is a massive need for accurate digital twins, especially in physical and the corresponding silicon. That's going to drive that, Devgan said. This is why we invest in digital twins for the data center, for simulating the entire data center. This is a non-traditional product, but it has become super important, applying safety and simulation and AI to optimize the data center. We even applied it internally to our own data centers. The things to remember about data centers is that it's not only these big cloud companies. There are a lot of data centers in the enterprise. When you apply it to our own data centers, we got 10% better power, which is usually because there is not much science applied to the design of data centers. There is an immense amount of science applied to the design of the chip, the rack, and all the networking. But how do you place the data center? How much cooling do you use? Is it overcooled or undercooled? And do you maintain it regularly? That's not done with that much science of the designing of the chip. So once you have a digital trend over the data center, you can do a lot of more optimization. The concept is well understood, but despite some early successes, discrete digital twins are still a work in progress. Digital twins is not a monetized system yet, said Allo. It's a collection of pieces. It's got elements of software, semiconductor, package, and board to the electronics, but there is an electrical effect where we had as part of the mental things like wire harnesses and a network connectivity. You've got the mechanical piece and a much more expensive portfolio of the multi-physics associated with that. Then you've got product life cycle management, because these things have to be built with a bill of materials. The completeness of all those individual domains from one company allows for some insights. There are still gaps when you bring the whole portfolio into manufacturing process simulations and things like that. How do you set all of this up for actual production of the end product, where all these systems get integrated? It's a lot to unpack. Progress is being made, but it's not push button, one size fits all solution. As in industry, we've been talking about it for a while, but it's essential given the complexity of how to simulate in real time, analyze and optimize it at the system level, said Getzi. Point to applications such as a data center and automotive as the key markets for this technology. As we start to engage deeper with the complexity of automotive and autonomous driving, the digital twins need to model both the electronics and the surrounding environment. In the case of the automotive, we have to partner with the ecosystem. They have other parts that need to come in with the chip virtualization and electronic system. Case in point, Synopsys partnership with IPC, which makes automotive simulation technology. We were able to virtualize and model the control system and the journal and the computer ECU to communicate with each other. Gage said, we provided the electronics, virtualization, and IPG brought in the surrounding physical world. During the execution of software development, testing team can be observed the behavior of the silicon into the environment for a specific workload they are building. And that does not only apply to cars, drones, data centers, and etc. All benefit from the virtualization, and we bring it closer to a silicon and 3D ICs or advanced packages sophisticated complex system. You need to take into account not only the electronic design. You can argue the electronic design and the case is understood. But the moment you start stacking chiplets into this advanced package, you're dealing with a worldwide other slew of challenges and be it dumber, mechanical, fluid, and structure. The AI revolution has become